So what is a professor of physics doing, suspended in midair like this, coming into the Royal Institution from the roof? Well, you may well ask. It's to make a serious scientific point. There's 10,000 billion tons of the Earth down there, pulling me down by its gravity. And this slender rope above me is resisting it. The electromagnetic forces in this rope are counterbalancing the pull of the entire Earth. Now, let's release myself. Oh, I'm glad that's over. Now, this is a live show, and if I don't get this off in the next hour, the next programme gets delayed, and Bryson will show me how, I'm sure. Gravity is sort of a thing you take for granted, and that's why we decided we had to make it look a bit different this time, and different it certainly is. Dramatic stuff. Now, it's really safety conscious, this, so I've got these things to take off. Thanks very much. I think that's where I stop. So, gravity, the force that's most familiar to us. It makes people fall to the ground, thankfully rather slowly on that occasion, and it acts across the whole universe. In fact, I've brought the solar system here to the theatre to show you. This beautiful thing here is called an orrery. It's invaluable. I'm treating it very, very carefully. Can you see the moon going around the Earth and the planets going around the sun? Here's the sun in the middle. The Earth, not to scale, by the way, and the moon going around it, and the outer planets here with their own moons. So this is gravity acting across the solar system, right the way across space, making everything orbit around the sun. Now, the sun itself is orbiting around the galaxy, and the galaxies are also orbiting around the universe. Gravity is ruling this whole huge show that you see here. And that's gravity in the big scale. But you can take very careful measurements of exactly where the different planets are night to night, month, year by year. And what they found 100, 200 years ago was that things didn't seem quite to be going right on the very edges of the solar system. All they knew in those days was as far as Uranus. And they found that they seemed to be wobbling very slightly compared with what they ought to be. They really understood gravity. Something was missing. And from that, they deduced that there were further planets beyond Uranus, and now we know of Neptune and Pluto. So that's an example of gravity really being understood and being used to deduce that something you haven't seen is out there. Now, the same thing is happening today. We have whole galaxies in motion, gravity pulling on them just like the planets are down here. And we find that the galaxies don't seem to be quite moving as you expect them to. There's some dark matter out there. Huge tracts of the stuff pulling gravitationally on the stars and the galaxies, which we have not yet seen, but we have begun to be aware of them because of the knowledge we have of gravity. So, that's gravity, the most familiar force right the way across the universe. The electromagnetic force, the very powerful thing that stopped me falling straight to the Earth, that is what's going on inside us at this moment. Everything that's solid, the shapes of everything, the planets, you and me, everything around us here, those solid shapes are the result of the electromagnetic forces inside us, gripping all the atoms together very tightly, resisting gravity. So, gravity and the electromagnetic force, those two major forces with us right now. It's the electromagnetic force that makes the floor solid, so that we don't just carry on straight down to the centre of the Earth, that something gets in the way. And that is really what we're doing today. We're going on the trail of the forces. We're going right back into the very first moments, to the moments even before the primeval quarks were made. We're going back to within a billionth of a second of the Big Bang, just before matter began. And this was the period when the forces ruled. And it's on the trail of the forces today. We're peeling off the very last layer of the cosmic onion. We've come down through atoms to the nucleus, to the protons and to the quarks. And we're peeling off that last layer today to see where the quarks came from. How were they created, the primeval seeds of all matter? Now you can see from this that we're getting very near to really deep questions about our origins, about how did things begin? What drives it all? Where do we all come from? Now, we're not the first people to ask this question. In fact, every culture throughout history has asked this question one way or another. And it goes back throughout all literature. Let's go and look at an example here. This beautiful picture shows the Hindus' idea of creation. According to them, there was this milk everywhere, the unformed universe. And here you see some of the gods churning the milk, the forces at work, forcing the milk around, turning it into the structured universe we have today. They didn't tell us where the milk came from. That's sort of put in at the start. And what we've got over here, this is a Dogon door from West Africa. A beautiful door that you find on the front of the granaries out there. This tells their own myths of creation and history. On the front, you see all these figures. This is actually a genealogy of the people. They've got their own history right the way back to what they believe the start of time to be, on the front of their granary doors. Now, according to them, the original granary was brought to Earth by a blacksmith who came down from heaven. He slid down on a rainbow and brought the grain with him and everything that you need, like fire and iron, all the ingredients needed to make the day-to-day universe. But where the rainbow came from isn't said. And the one that's most familiar to us, perhaps, is the biblical tradition, the Old Testament. It says, there was darkness on the face of the void, and then let there be light, and there was light. Compare that with what we have today, the sort of perception of the Big Bang. If I was asked to summarize the Big Bang in just 2 sentences, we would say, once upon a time, there was no time. That's before the Big Bang. And then the Big Bang happened and time began. Now that's a 2-sentence summary of the present perception of the universe by 20th century science. It's not that different from there was darkness on the face of the void. Once upon a time there was no time. And let there be light and there was light. The Big Bang happened and the universe began. So there's great similarities there, but there's also differences. The crucial differences are that by experiment we can go back to within a billionth of a second of when that light turned on, when the Big Bang happened. I don't know what happened before it, but from that moment onwards, we can, by experiment and looking, recreate the progress of the universe from that first moment up to now. And that's the journey that we've been taking, right down to that first moment. But it is, in my opinion, quite important here to recognize how near we are to the boundaries of science, between science and myth or philosophy. And Peter Medawar put it very nicely. He said, there are some questions that are beyond science to answer, such as, what's the meaning of life? I mean, that's the sort of question that science isn't supposed to be able to answer. Or, what happened before the start of time? And he said, only charlatans will profess to answer those questions, so I shall not. I shall stick that as my definition of what we can discuss and what we can't discuss. So I don't know how that Big Bang happened. I don't know how that light turned on, but once it was there, we can progress and work out how the matter was created and brought through to the universe we now see. And that's what we're doing today, that final layer of the cosmic onion, how the light turned into the matter that we're created from. So, let's do something we're familiar with to draw an analogy with language and what we're doing here today. So, we all know about language. All of literature is built of words, which ultimately are built of just 26 letters. And you can arrange the letters in different ways, and you build up different words, such as these two here. And with the same letters, I can move them around and make other words. So, there you have it. So letters can make many words. That's the first step. But now let's come to the second step. Words making up phrases and sentences. So let's put a few up here, and then we will use the grammar, the forces of language, if you like, to arrange those into a well-known phrase or saying. Any volunteer that can help us find the solution to this? Would you like to have a go? What's your name?
Alice.
Alice, right. Can you arrange those using the rules of grammar to make a well-known phrase or saying? That's right. Oh, you've seen it too, right. Has to boldly go where none has gone before. Terrific, thank you. So, does everybody agree that using the rules of grammar, that is the solution to the puzzle? Well, it's the solution to the puzzle, all right, but the national curriculum would probably require us to put it like that. So, what is this analogy? Well, the letters have built up the words, just like the particles build up structures. And the grammar forces those words into meaningful sentences and literature. Just like the forces of nature move these structures around and build up the large-scale universe, the universe that we're familiar with. So we're going to look at the forces. And we're going to meet four of them. Thankfully, the only four. Fundamental four forces. Let's begin with the one we know best, gravity. Wow. If that is Isaac Newton, he'd still be working it out. Gravity, the famous story of the falling apple and Isaac Newton coming up with the idea 300 years ago. And pretty well, the idea that he came about all those times ago is essentially true today. Gravity, the same force that makes apples fall on people's heads, also acts right across the universe. It's that same gravity that today we know is acting on the galaxies, and with supercomputers we can even see what gravity does. Here is a supercomputer image of two galaxies, tens of thousands of stars, each one of which is pulling by gravity on the others. And you see the two galaxies gradually get pulled together by that gravity. And as they do so, the stars in the middle start getting pulled away. Tidal forces, the same source of forces that you see raising the oceans day by day, making the tides here on Earth, are acting right the way across galaxies on the supercomputer, just using Newton's law of gravity to work out the consequences. And you see, at the end, you get a very distended structure with wings right out here. But in the middle, where most of the stars are, they now start getting pulled together again by the same forces of gravity. Until at the end, you've got a very remarkable structure that you wouldn't have imagined if you hadn't been able to work it right through. Then you take your telescope and you look into the sky and you see real galaxies. And you find shapes like this that you might not understand if you didn't have the supercomputer to show you that using the laws of gravity, the ones that we understand, the falling apples and so forth, acting right the way across millions of miles, leads you with these wonderful structures of galaxies that you see in the sky. So that's gravity at work in the really large scale. So that's the first of our forces, gravity. The second one is electromagnetism, the force that was in that rope that was stopping me falling to the earth, the force that makes things solid and gives things shape. Now, electromagnetism is like gravity in that it spreads over very large distances. But it's got another feature which gravity doesn't have. In gravity, everything attracts everything else. But for the electromagnetic force, there's two parts. Like charges repel and unlike attract. Let's see this demonstrated by Bryson's device. So this is a beautiful old machine that we're going to use to put electric charges onto these two spheres here. It'll put opposite charges, positive on one of them and negative on the other. It'll take some time to charge up, but what you will see is that when the charges on it are big enough, the attraction will pull them together, and then they'll hit violently. Let's see this getting charged up now, and gradually, here they come, and a spark jumps. Now, the moment they touch, they discharge and bounce away. The charge builds up again and pulls them. So here you're seeing the attraction of opposite electrical charges, right there before your very eyes. Thank you. So that's one half of the story of electromagnetic charges, electromagnetic attractions and repulsions. That was attraction of opposites. Now we've got the repulsions of like charges, and that creates a problem for us. Let's just think, we're all sitting here quite happily, nothing untoward happening to us, not exploding or anything. But inside us are atoms, and in the middle of the atoms are nuclei, and here is an enlarged picture of a nucleus with lots of neutral particles in it, but also lots of protons, each one of which is positively charged. Now, like charges repel. So each of these protons is repelling all the other protons. The nucleus then should be exploding apart, yet somehow it stays together. Now that's a puzzle. We'll come to that in a moment and find the answer to it, but first of all, let me give you an idea of actually how strong that repulsive force is. Bryson's next demonstration is going to show us the repulsive power of electromagnetic forces. So, what we're going to do now is first of all cool down this ring so that we make the effect rather more dramatic. And we've got a magnet here which will turn on when Bryson throws the switch, when everything's ready. Okay, don't spill it over me. This is about as cold as, well, the universe out there now. Are you all ready? Oh, this is going to be really dramatic by the time it gets going. Right, here it is, ready to go. Put it on the magnet. Now, turn the magnet on. Okay, do you reckon we'll try it again? Well done. So, you saw there the power that magnets have got when you can make things repel. In fact, it sent the thing almost as high as I came down from at the beginning, and then it came down rather faster than I did. So, that's the repulsive power that you saw there with a large-scale magnet. Just imagine now, then, the strength of the repulsive power buried in the nucleus. These things are really small, pretty well touching, and each of them repelling with at least as much power as you just saw. So how come we are still sitting here happily without our nuclei exploding apart? There must be something very, very strong here, another force, a very strong force gripping the nucleus together and overcoming that repulsive power. Let me show you what we believe today that's caused by. So here is a picture of a nucleus opened up, and you see the three quarks buried inside one of them. And the strong force that binds the quarks together is shown here by these little wiggly lines to give the impression of the things really being gripped. Now, this force is so strong that it leaks out very slightly. We show this on the outside here, and grips the individual neutrons and protons together. So it's that very strong force, rooted in the quarks, that holds the nucleus together and resists that outward thrust that we saw the demonstration of. So that's three of the forces: gravity, electromagnetic forces, and now the strong force. The strong force only acts in and around the nucleus. You don't feel it at long distances, though the fact that we're still sitting here happily tells us that something's going on inside. And so now I come to the fourth, and thankfully the final force. It's called the weak force. It's not really weak, it's just weak in comparison with that strong one. But it's the force that manifests itself in radioactivity. That rock is undergoing radioactive decay, and you're hearing the effect of this fourth force with this Geiger counter. In fact, this little demonstration is showing you all four forces at once, because here's gravity, and my hand stopped it because the electromagnetic forces make my hand solid and get in the way. The strong force is at work because it's not exploding, it's being held together. And there's the weak force, you're listening to it. Now, that's a demonstration of all four forces. In fact, all four forces are at work all the time. When you walk to school, when you're walking down the street here, sitting here around the room, all four forces are in operation. Gravity's pulling you down. The solid floor, electromagnetic force, is stopping you sink right through to the middle. The strong force is keeping your nuclei together. And the weak force is causing radioactivity. For example, what's going on in the sun? The weak force is part of that. So all four forces are operating all the time, everywhere. So, what we've got is this modern picture that the whole of the universe is driven just by the four forces. Now comes the question, but how do they actually work? I mean, let's just think a moment. We started off the talk, I was right there in the roof of the theatre. The Earth was down here. How did the Earth know that I was up there to be pulled down? Now, our modern ideas are that something goes between these particles as they move around, that an agent transmits the information, a carrier of the force. Let me give you some examples of what appear to be forces acting at a distance. There's a beautiful little thing here. It looks like a toy, but in fact it's a historic scientific instrument. And I want you to look at the little black diamonds inside here. Now, at the moment, they're sitting quite still. And if Bryson turns on this lamp over the other side here, I can perform magic. You see, by moving that card, I can make those things move around without touching them. Just watch. And if I move the card back again, they will gradually slow down. Now that's magic, right? I made the things move around without touching them. Let's look at this demonstration another way. Let's look at this Bryson special behind me. This is a bicycle wheel whose spokes are made of elastic bands. Now, Bryson shined the lamp on it. What happens is that the wheel very gradually begins to move. Nobody's touching it, it's beginning to move. A force must be acting on it. Now, what's going on is that elastic, when you warm it up, it actually contracts. And the elastic on one side where the light is shining is contracting and pulling differentially across the wheel and making it start spinning round. So you're seeing this apparent action at a distance. What is actually happening is that heat is being transmitted to it. So an agent is going along. Thanks, Bryson. Now, our best theories, indeed, today suggest that something goes from one to the other, and the something are little particles. In fact, the first demonstration, when we shone the lamp that my card was obstructing, the moment I removed the card, the light from the lamp was shining on those little discs and made it rotate around. And so little particles of light were going from one to the other and transmitting the force. In fact, we believe that all of the forces work this way. that there are hidden agents that travel between one bit and the next and make forces happen. And we can demonstrate that here in the room now. And for this, I'm going to need a special floor brought in. So here's the floor on which we're going to demonstrate the action of the forces in modern theory. And we're going to have 2 chairs, and we're going to need 2 volunteers. I need 2 people of very similar weight and height. Could you 2 come down, probably? Hi, what's your names? Ben. Hi, would you like to sit on this side? And you're? Toby, you sit on the other side. Now, place them very carefully facing each other. Feet off the ground on there. Right, now, you're initially quite still. If you hold that, what I'm going to ask you to do is gently throw it across the other side, and then you throw it back, and let's see what happens. Okay? Let's go. Gently. Okay, stop. Thank you. Right, you've got to bring yourself back. Give it a second go. So what you see what's happening is that as the ball goes backwards and forwards, they start moving apart, as if a force is acting on them. Okay? Give it a go. Right, thank you very much. So that is what we believe is going on. We believe that all of the forces involve the exchange of particles. If you were looking at the demonstration there from far, far away without your spectacles, what you would have seen would apparently have been 2 boys in chairs sitting quite happily, spontaneously moving apart from each other. Of course, when you were able to look at it very closely, you saw that what was causing that movement apart, that force between them, was the ball going backwards and forwards. That ball was like the particle carrying the force. Now, that's an incomplete demonstration because it only shows repulsion, but attraction also, we believe, happens this way. Now, it's not just a case of believing. In the case of the electromagnetic force, we've actually seen the agent, the particle that gets exchanged. It's a little bundle of light, which we call a photon. Now, what about the other forces, the weak force of radioactivity and the strong force? They also have little particles that transmit them. But to find out and see those particles, what we've got to do is to go back to those very first moments when the forces ruled. It's only under the conditions of the extreme heat of the first billionth of a second of the Big Bang that we have the hope of seeing the force carriers of all of the forces acting with equal strength and equal vigour. So what we've got to do is to recreate these incredibly hot conditions that were present just before matter began and do it in the laboratory. Now, how are we going to do that? Well, first of all, what's heat? Well, heat has got many forms, but one of them is all the bits and pieces whirling around and bashing into each other very violently. And it's that we're going to do. We'll build a big accelerator to accelerate particles to almost the speed of light, and then we'll clash them together, head on, very violently, to recreate the sort of conditions of that original heat. And it's in those experiments that we have the chance of seeing those particles that carry all of the forces. Now, first of all, let's get the idea across of what's involved in clashing beams of particles together. So, we're going to need to set this up, and I think what we ought to do is to remove, first of all, this very valuable device that's here on the tabletop. And Bryson has dressed specially for this demonstration in his CERN duty physicist t-shirt. Thank you, Bryson. Okay, right. Can I have 2 volunteers? Right. Well, I think you 2 are in the safest seats because everybody's got spectacles on around you. Hello. What's your name?
Rebecca.
Right, Rebecca. If you will hold this gun over here, and you're? Matthew. Okay. You come over and stand on this cross just here, and this is your particle accelerator, and you've got your own particle accelerator over this side. Now, let's make sure we're all standing at the right place and that I'm safely out of it. Right, there's a ring here that is the sort of target. What I want you to do, we're going to power this up in a minute. When I say go, see if you can fire both of your accelerator particles through that ring, and if we're lucky, some of them might hit each other. Okay, let's go. Thank you. Well, believe it or not, that is pretty much the sort of thing that we do in real experiments. We have two beams of particles, subatomic particles, each of which is moving almost at the speed of light, firing in at each other, and just like there, most of them miss. Occasional ones hit, and it's the ones that hit that tell the really interesting story. Now let's see where this sort of thing is done. This is an aerial photograph just outside Geneva in Switzerland. The French-Swiss border is marked in dots all the way along here. And this huge circle here shows the outline of the accelerator at CERN, the European Centre for Nuclear and Particle Research. Now you can see how large that thing is by comparing with the runway of Geneva Airport that's down here at the bottom. Now the accelerator has to be that large because that's what you have to do to speed the particles up sufficiently, because what we're trying to do is to recreate the conditions of the Big Bang. And you need a big accelerator to do that with. Now the actual accelerator isn't on the surface because that would involve driving the thing through people's back gardens, and that's not too easy to do. So it's built about 50 metres below ground. 50 metres isn't special, it's just that that was where the geology was the best to make this huge device and make it all flat and so forth. So this is the accelerator, the outline of the accelerator that's going to recreate the Big Bang for us. Now let's go downstairs and have a look inside it. So here is a tunnel which is in dimension about the same size as a tunnel on the London Underground. You can see two people standing here, which is setting the scale. And along here, these boxes are actually magnets that guide the particles around this huge ring. It's 27 kilometres all the way around. And inside these magnets is a small tube about 10 centimetres in diameter, and the particles live inside that tube and go all the way around that ring. The tube is evacuated. It's like being on the moon. There's so little air inside it because you don't want the particles to get obstructed as they go around. They're crossing the French-Swiss border about 11,000 times every second, but the customs decided not to bother about that. So that's what it's like down there, and we have made our own accelerator here in the Royal Institution. And can I have a volunteer to help me drive this? Would you like to come down? Hello, what's your name? Hi. Right, let me show you what I'm going to do. If you will operate the yellow dial here, when I tell you, start moving it very slowly to the right. That'll speed things up. Don't start yet. I've got to start the beam going. So let's get the beam going very gently. OK, now it's going nice and slowly. Now start speeding it up. A bit more, a bit more, a bit more. Let's get it to its maximum. That's it. Lovely. Hold it there. Thank you. Well, as you see, high-tech accelerators are not easy, but when they work, they get you there. And at the collision, there's this great annihilation, and trails came pouring out, and we've captured them for you here on the picture. So, it's the trails coming out after that collision. They are telling the story of what happens in that Big Bang, or in this case, that little bang. The trails show us that interesting things have happened. They don't actually show us matter being created, but they show us where the matter has been. Let's look at another picture here, which gives us an idea of the sort of things. So, in this picture, energy has come shooting in from here, and it's not an electron which goes spiralling round and round. That's a thumbprint that we all recognise in particle physics, the sign of an electron, spiral. Now, the reason it's spiraled is because a magnetic field has made it go like this. But what's this on the other side? It's a spiral just like that, but all exactly opposite to it. This one is going that way, and the other one is going that way. The first one is a negatively charged electron, matter, the stuff that's in all of us. The other one is a positively charged version of the electron, equal and opposite. It's antimatter. We call it a positron. It's got exactly the same mass as an electron, but equal and opposite electrical charge. And that's the wonderful key. It's electrons and positrons that if we can scale them up to a huge machine, we can put them to use. And we've got here a model of what it's like if you go down to that huge machine at CERN, deep underground. And here we've got the magnets that will send a beam of electrons around, say, clockwise. But the very same magnets can send the beam of positrons around anti-clockwise, antimatter, anti-clockwise. And that is really neat. That's the key to this whole thing. That the same set of magnets will send the two things counter-rotating, and then you can bring them together and make the collision, recreate in that annihilation flash the first moment of the Big Bang, and see what happens. Now, you probably all heard about antimatter in science fiction, but it's real stuff. We use it all the time. You probably also know the story that if you're an astronaut and you go out to some star far, far away, you better check that it's a star made of matter and not something made of antimatter. Because if it's antimatter and you go rushing across and you see your anti-self and you shake hands, so the story says you both disappear in a flash of gamma rays. But it's actually not quite as bad as that. Your hands will disappear in gamma rays, but the rest of you are pretty well untouched. But that is what we're doing. We're firing beams of matter one way, antimatter the other way, annihilating them, and that's recreating the heat of the moment just before the matter that we see today were made, out of that original flash. So that is what we're trying to do at CERN. Let's see what an electron in that ring sees. So here's a view of electrons. Each of those bubbles represents a zillion electrons, all shooting along in the center of the 10-centimeter tube. So this is inside the magnets, speeding them up until they're going almost at the speed of light, fast enough that when they collide together, they will be able to do the job we're wanting, namely reproduce that first moment, and then we can see what happens. Now, what they're doing is heading towards the detector, the special camera that's going to record the collisions for us. Well, matter we're all knowing, but let's just first of all begin with a familiar piece of antimatter, namely my twin in the anti-world. This is the world's most powerful telescope, because with it we can zoom back through billions of years of time and catch a glimpse of the start of the universe. Now, the beauty of it is we can do it time and time again, so it makes it an incredibly powerful time travel machine. Science fiction's got nothing like this. Now, the only way that we know how to recreate the immense energies and temperatures that were present in the first moments of time is to make a sort of subatomic train smash. We use tiny pieces of matter, electrons, and we smash them into tiny pieces of antimatter, positrons. Now, that's not easy. There's super powerful magnets like this all the way around this tunnel, steering the electron beam, negatively charged, that way. And the really clever bit is these same magnets can steer the positively charged positrons that way. So it brings the two beams around the circle into this violent collision that recreates the first moments of the universe. It's about 27 kilometers all the way around the circle, and the particles have gone round about 1 million times since I've been speaking to you. So I've got to get off to see that collision because they're moving nearly at the speed of light. Well, my anti-twin is always exaggerating. It doesn't seem much like the speed of light to me. Anyway, so he's heading off towards the detector. And here my colleagues at Rutherford Appleton Lab have made a model of the detector. The particles, the electrons, come shooting in from this end, and the antiparticles, the positrons, come shooting in from that end. And in the middle is where they meet, collide, and annihilate, and make that momentary flash, that reproduction of the Big Bang. Now, out of that, matter and antimatter emerge in equal amounts, and they go shooting out across the detector. Now, we've got to capture those things and look at them. So we've got huge magnets around the outside here that will bend the negatively charged particles one way and the positively charged ones the other. And we can also tell how fast they're moving. If they're going very fast, they bend very little. If they're going slower, they'll bend a lot. So inside here, there's sophisticated electronics. In fact, designing detectors like this is a challenge in its own right. You're making a high-tech challenge to science and technology to invent new ways of capturing these ephemeral particles, detecting them, showing them. Electronics inside here records them as they go past, and they send the information to a computer, which is like the eye that we'll see at the end of the telescope. And the computer will then turn them into trails that are visible, and you can see them presented here, 3 trails shooting out from the central spot. So this is a model of the detector. The actual detector we would have brought along, but it wouldn't get through the door. It's about 10 metres high, which is sort of up to the roof, and it's about 10 metres long, which is pretty well across the front of the theatre. But my anti-twin is going to it, so let's see how he's doing. This is the machine that takes the photographs, and as you can see, it's no ordinary camera. It's as tall as a cathedral. And for many particle physicists, this is the most exciting place in Europe to be right now. We call it the detector. Normally, it's all closed up, but they've taken the end caps off for us so that we can go inside. This is the nearest that humans have ever got to the Big Bang, right there. The antimatter, the positrons, come in from this side, and the electrons come in from the other end. And when they meet, they annihilate in a flash of energy. And that's the key moment, because for a fraction of a second, you're replaying the Big Bang at the start of the universe. Now, out of that flash of energy stream particles, just as particles streamed out originally at the start of time. And they flash across this detector, which is 10 meters across. But they're moving so fast that they're out of here before you can say E equals mc squared. So we have powerful magnets that slow them down and bend them just enough that we can capture their passage. But at the end of it all, we're really reconstructing the scene of a car crash from the skid marks on the road. Now, the jumble of signals from the debris flying right across the face of this detector go down these cables into the computer room, and that's where we're going next. Well, this is where we work out what went on at the scene of the smash. And it's a pretty confusing picture. There's trails all over the place. And this is where the computer has really revolutionized particle physics. 15 to 20 years ago, you would probably look individually at maybe 500 pictures in a year, looking for the one or two that told the really interesting story. And if you had a bad day when the critical one came along and you missed it, that's your Nobel Prize lost. Whereas now, the computer can analyze thousands of these every hour. And what's more, it's programmed to look for the very interesting ones, and then you can spend more time studying those in detail. George Charpak got a Nobel Prize recently for developing this revolution. Indeed, that's a very important part of the story. We hear a great deal about accelerators, setting up the conditions to replay the Big Bang. But we hear rather little about seeing the results of it all. And it was the development of these new special cameras, the use of computers and modern electronics to make visible these things that have really revolutionized much of our science. Now, as it was saying there, these signals are sent down the cables to computers. They're flashed all around the world. Scientists all over Europe and America even are analysing these things in their home laboratories. And we couldn't bring the whole thing with us here today, but we have got the eyepiece at the end of the telescope, a real computer that's been brought here. My colleague Neil Geddes from Rutherford Lab is going to show us some things from this. So to begin with here, we've got a whole stream of noise on here at the moment. This is the raw data that's come out of the machine. The collision point is right in the middle, and these are all the raw signals that the computer has received. Can you clean them up and get some real trails to look at? So the computer is now sort of responding to Neil's commands, and it's finding now the trails of the particles. That you see them shooting across the central part of the detector, leaving the blue lines out from the collision point. And on the outside, you see these yellow boxes. Now, what they're showing is the amount of energy, the amount of punch that these things have when they hit the edges. So the big yellow boxes mean a lot, and the little ones mean a little. Now, the interesting physics in this is in the ones that are really carrying the biggest punch. So can you now tell the computer to throw away the sort of uninteresting ones and see where the real punch is? And after doing that, we've now got 3 separate sprays shooting out from that central collision point with huge deposits of energy at each end. So that's what we've got so far. But we can do more. Let's zoom in and see if anything interesting is happening right there where the Big Bang happened. The computer's now taking us on a voyage right to the heart of matter, to the very moments of creation. Let's see what happens. Right, so this is as far as we're taking it. The trails all track back, but you see these 4 cross at that point. Now, everything from here into the centre is not real. The computer has just drawn those lines in. The real action starts here. That the annihilation that set up the mini Big Bang is there in the middle, and there's a gap before the interesting particles appear. What this gap shows is that an exotic form of matter has lived for maybe less than a billionth of a second, and then it has changed its form and produced the particles that the computer picked up. You see it there as a big gap, and there's a little one there which lived even shorter. So in this computer image, you're actually seeing not just the particles that we're made of today, but also recovering for the first time since the original Big Bang, the presence of very short-lived things that died out in those first moments. By recreating time and again the Big Bang in the collisions at CERN, and having this huge detector camera to see what happened, you can then bring them to the eyepiece. So you're looking in the eyepiece and seeing how matter was created in those very first moments. So thanks, Neil, for bringing that along. Now, there's hundreds and thousands of pictures like that we've gathered over the last several years, and gradually we're beginning to decipher the story that they tell. We're discovering some interesting things. Let me just show you a couple of ideas. So, one of 2 things tends to happen pretty well all the time. There's a big flash happens, that we've set up the collision, the annihilation, and it's what happens afterwards that we're looking for. So what happens most of the time is that a particle will go shooting out from this in one direction, and an antiparticle will balance it on the other side. It might be an electron shooting out and a positron going the other way, or it might be a quark shooting out and an antiquark shooting the other way. It doesn't seem to care which it is. It's always the same. The other thing that happens is that after that flash, a particle goes shooting one way and an antiparticle the other, but suddenly it changes direction because the force carrier has been emitted. So you see matter, antimatter, and a force carrier, making 3 separate trails coming out. Let's see what they actually look like in real events. So here's a picture of an electron and a positron shooting out in opposite directions, depositing a huge amount of energy in the yellow boxes at either end. That's a back-to-back electron. Now let's look at a back-to-back quark and antiquark. Doesn't quite look the same, but you can see back-to-back, the quarks hide themselves. We only see their trails. They're like my cat when it's raining outside and I want to throw her out and she won't go. I find the foot trails on the floor and suss her out. It's like here. The quarks are long gone. They produce particles, a shower of particles, but the direction of the showers show where the quarks were, like the fossil remnants that led to these things. And the third one here shows us what happens when the force carrier, here's one where we've captured the force carrier as well. 3 separate sprays, just like the sprays that we saw in Neil's computer. So from all of these things, we've begun to discover that when you set up the original moment of the universe and see how matter and antimatter appeared, it seems that the electrons and the quarks behave pretty well the same. It's almost as if there's just one type of matter deep down there. And when we look at the force particles, we find that they seem to behave the same as well. So that is where we have come to, revealing the last layer of the cosmic onion. And now we can really begin to put it together. This is a big moment. Bryson, give me my cloak. Like a magician, we're going to reveal to you the whole universe in the theatre. Okay, we're ready to go? Get the electromagnetic radiation working here. Terrific. Right. Bring on the universe. The universe is a hat. And we are going to reveal from the hat, like a magician, the particles that make up the universe that we know. Let's begin with an up and down quark, which we'll put here on our chart. Is there any more? There's a charm and a strange quark, which we'll put just here. 2 by 2. Interesting. Let's see what else nature provides us. Ah, this is interesting. 2 by 2, but one we're still looking for. But it's the 2 by 2 clues that's putting us on the trail. Let's see what else we can find. An electron and its neutrino. Now, this lot here, by the way, is sufficient to make the universe around our parts. Up and down quarks, the nuclei in the center of our atoms. The electrons whirling around on the outside of the atoms, and these ghostly neutrinos emitted in radioactivity. 2 by 2. Let's see what else we've got. Oh, we've got something called a muon. A muon, what's that? It's a heavier version of the electron, identical to it in all respects, but it's 200 times heavier. Don't ask me why it's there. What else have we got? I'm getting the message here. Nature's done it again. There's a third one. We call it a tau. Exactly the same charge as the electron and the muon, but heavier still. And yet again, a neutrino with this, a neutrino with that, a neutrino with that. 2 by 2. The quarks, 6 of them, and the electron and its friends, 6 of them. And that's the lot. We know there's no more. The experiments of CERN have shown us that that almost certainly is the end of the cosmic onion voyage for matter like this. What about the forces, the force particles? Where are they? Well, there's a particle to carry the gravitational force. We know it must be there, but we haven't yet found it yet. We're still searching hard. What else have we got? This is the carrier of the electromagnetic force. Light. We know all about that. What else? Ah, this looks like the carrier of the strong force that holds the quarks inside the nucleus and grips it all together. Any more? Yes, the weak force, the radioactivity that causes the sun to burn and things to change form. And that's it. The universe on a board made of plastic. Up and down quarks, and the electron and the neutrino, 2 by 2, is sufficient to make everything around here. And our theories seem to be quite happy if that was the end of the story. Why it is that nature has made a photocopy and another photocopy, we don't know. But we're so sure that this 2 by 2 pattern is the answer that although we haven't yet found this guy, the top quark, we pretty well know where to go and look for it. And that's what we're on the trail of at the moment. So, that's the universe as we now know it. Now, in this particular lecture, I can probably go just beyond the boundaries of science and even show you from our material universe to the Big Bang what happened before the Big Bang. And here it is. Bipin. So, there it is. We find that there are 6 basic particle types, whether they're quarks or whether they're the electron and its friends, and they go 2 by 2. Why it is that nature wasn't satisfied with just one set and had to do it 3 times is one of the puzzles. But apart from that, is that the whole thing? Have we got it all sorted out? Well, nearly, but not quite. There are a few little pieces of the jigsaw puzzle still to be put in place, such as, where did antimatter go? Everything that we have seen coming out of those detectors at CERN have made matter and antimatter in equal proportion. So where did all the antimatter go? It's matter around here that we're made of. The antimatter's disappeared. How? And where does mass come from? We don't know that. So those are sort of questions that we still need to answer. It's possible that we have indeed got our feeling of the theory of everything right waiting there, and that these are the last two pieces of the jigsaw that when we put them in place will complete the picture. Or it might be like 1893, when they thought they had the theory of everything and the little bits missing turned out to be huge gaping holes that gave rise to the whole of 20th century science. Who knows? It's those questions that we're going to have to address next time. See you then. Hey. Oh, not him again! Get away!